Just a couple things before we start. If you managed to finish your Lab 5 checkoff but didn't get a beta sticker, a beta inside sticker, and you'd like one, I have a bunch down here, so come see me and I'll be happy to hand them out. There is a quiz tomorrow in section, and I'll have a hint for you at the end of lecture. Help me remember. So if it looks like I'm finishing up, you should yell hint in a large voice, and I'll be happy to be forthcoming. So what we're about, starting a little bit last lecture, but certainly for the next 4 or 5 lectures, is looking at the rest of the system architecture that's needed to build the sort of machines that we all sit in front of all day. Some of us many, many hours every day. One of the original sort of popular time-sharing systems, one designed for a new class of very affordable computers, was Unix. Unix was the brainchild of Dennis Ritchie and Ken Thompson down at Bell Labs in Murray Hill, 3C, 3rd floor, building C. They invented a lot of things, actually, as it turns out. To have a good language in which to write their operating system, they invented the language C, which we all we either use it or we use some language that inherits from C. The name Unix is sort of inspired, unlike the cartoon, is sort of inspired by the Multics operating system. So when I first came here many years ago, Building 39 was the computer center, and there were 2 large machines. There was a huge sort of corporate IBM, and there was a GE Honeywell 645, which was a very modern architecture. Even for today, it would be a modern architecture. It had many pieces of interesting hardware to do interesting memory management, a segmented address space, and capabilities and protection rings, and it had. Anyway, there was not very many concepts that even today we have in time sharing that weren't exhibited by the Multics operating system. But when this new generation of much smaller, more affordable machines came out, one of the things that people were interested in doing was having the advantages of an operating system, and we'll be exploring those over the next couple weeks, to actually organize the use of a computer and share it effectively among all the things that need doing. But it didn't need all the bells and whistles that Multics had. So the sort of joke was that, Ritchie and Thompson would say, well, we don't know what an IC is, but Multics clearly has too many of them. And so we have a much simpler operating system, so we'll call it Unix. So, okay. This is as good as it gets with 004 humor. So, okay. So, alrighty. So let's sort of just do a quick refresher on virtual memory. So remember what the goal of the virtual memory system is. So this is actually a new piece of hardware we've added to our system. It's part of the memory system, as the cache is. Its goal was to basically introduce a mapping between the address produced by the CPU, which we call the virtual address, and the address consumed by the actual DRAM chips, which we called the physical address. Physical because it was actually sent to the physical memory chips. And what we chose to do was to basically divide our virtual memory, what we think of as just one large 32 or 64-bit address space, into actually a contiguous sequence of pages. So we're going to be mapping, a virtual memory addresses to physical memory addresses. That's what the job of the MMU is. But instead of doing it, byte by byte or word by word, we're going to be doing it page by page. And each page holds a collection of bytes, 4096 bytes or 1024 bytes or 16,384 bytes, but a handful of bytes. It's not millions and millions of bytes. It is not 2 bytes. And what we need is conceptually, and in fact, practically, the data structure we use to explain how the mapping works is a table, and most implementations of the memory management unit actually have an instantiation of the idea of a table, where we use the virtual page number. So this would be virtual page 0, virtual page 1, and it's really just the high order portions of the address bits to index into the table to collect some information about where in physical memory to actually find the corresponding physical bytes, where the actual DRAM locations that hold the 4096 bytes that are on our virtual memory page, and some extra information that would let us know whether or not that page was resident in physical memory, so the so-called resident bit. And that would be because there would be some times when certain portions of our address space were not immediately accessible. And we'll talk about that more in just a second. And then a dirty bit to keep track of whether we've written into a particular memory location, in which case we would need to write that page back out on disk before replacing it with some other page we needed to bring in to use our physical memory. Okay, so the translation process goes in a couple steps. We divide the address into a page offset, which basically is not part of the translation process, and the virtual page number, which is. The virtual page number is used as an index. What we're going to do first is have a very small, fully associative cache, typically 16 to 64 locations, in which we attempt to very quickly, the reason this memory is so small is so that it operates very, very quickly, and sort of the access time of a register sort of time, where we can basically present a virtual page number and hope to look up the physical page number, which would allow us then to marry the physical page number with the page offset and immediately go to main memory at the cost of picoseconds, or hundreds of picoseconds, or maybe at most a handful of nanoseconds. And so we have all the advantages of a complicated scheme where what we've done is we've cached the answer. So it's available at very high speed for us to use. If in fact we miss in the cache, we don't have a mapping for a particular virtual page number, then we're going to go off through a more complicated process where we use the virtual page number as an index now into a table, an actual physical table, often in main memory, which has in the 32-bit words of main memory, it has the same information. It has the physical page number and the resident bit and the dirty bit, and that will hopefully produce either an answer which says here's the physical page number if the page is resident, and then off we go. But remember, we've already sort of done one memory access to get this information, and we're about ready to now do a second, so this is not an inexpensive operation. So once we get this value, we tend to put it into the cache in the hopes that as soon as you start accessing addresses on one page, you're going to say, oh, wait, I'm accessing instructions. I'm going to be accessing other addresses on the same page. And so the cache hit rate here tends to be super high, 99% plus, because of the sort of super locality of references to pages. If the page is not resident, we basically turn the job over to software, whose job it is to bring it in from disk, and we'll see an example of that in a second, or to basically throw up its hands and say, I'm sorry, you haven't asked for access to that particular page in your memory, so you'll get what's a page fault or a memory fault. And we can all write programs that if you just randomly generate an address and try to access it in most operating systems, you'll get a page fault. You'll get a memory access fault. Just basically saying, I'm sorry, you need to prearrange with the operating system which portions of your address space are going to be available to. And that's clearly important in the era of 64-bit processors. So 64 bits is 4 billion byte address spaces. I mean, 64 bits is actually a big number. And so, you obviously just can't reach out to any one of those, however many exabytes, 16 exabytes, and expect to just be able to access it at low latency. So in general, the programs in the operating systems are forever chit-chatting about memory allocations. And we'll see some of that when we get a little farther into operating systems. Let me quickly run through a couple of examples. The first one is very simple. So this is a toy sort of example. So we have 8-bit page offsets. Here we have a 4-bit virtual page number. So these are 12-bit addresses. I used to make jokes that, someday we'll have a watch that has small addresses. And of course, now the Apple Watch has a full-blown exotic processor with, much more powerful than the beta. So it's hard to conceive these days that even the most trivial of devices seems to have a 32-bit or a 64-bit processor in it. So this is clearly a toy example now. And what we want to do is to follow the translation process. This is the page table, all carefully written out. And this is physical memory. And you can see that some parts of physical memory are already busy holding virtual page contents. And you can see also that there's no particular order in which the virtual page 0 happens to be on physical page 2, and that sort of jumbly, where in physical memory you are is really the luck of the draw. When it's time to start your program and we need to bring in virtual page 0 of your program, it's really just what's the next physical page that's available in memory for use. Okay, so suppose we go off and access a particular address. In this case, we're doing a load of address hex 2C8. So C8 corresponds to the offset bits, so they won't get translated. But we need to translate the virtual page number, which is 2, into a physical page number. So what do we do? So this is where, follow along at home sort of thing. You look at entry 2 in the page table. We're using the virtual page number as an index. And we look up and we see what physical page are we on? 4. It says so. And in fact, we're resident. So the resident bit is 1. And so that means this number here is the actual corresponding physical page. And so we're going to translate the virtual address of 2C8 into the physical address of 4C8. And that's actually what we asked the RAM to do for us. Okay. So there's example 1 of being MMU for a day. Here's a slightly more complicated example where I want to access virtual address 600 with this store location, with this store instruction. Okay, so you're good at playing MMU. Let's see if you can figure out what we need to do in order to actually end up completing the store instruction. Well, you're probably saying to yourself, okay, the address mapping, splitting the virtual address into offset and page number, I can just, the bottom 2 hex digits are the offset and everything else is the page number. So the page number here is 6. All right, here's the page number 6. If I go look in here, I have a 0 in the resident bit. So take a deep breath and think to yourself, what does it mean when there's a 0 in the resonance bit? In fact, you can double check your guess. If your guess was that means it's not resident in memory, and indeed in our little physical memory here, you don't see any references to virtual page 6. So what do we have to do? How do we actually go about getting it so that the memory, the hardware can actually complete this store instruction? Well, we have to basically go take what's called a page fault and deal with the fact that we have a missing page. So what we'll do is, the first thing we need to do is say, okay, I need to bring a page off a disk. So every program has its own sort of disk file that has the actual bits for all the possible virtual memory locations. So we're going to go to that file and pick up all the 4096 bits, or in this case 256 bytes that are in virtual page 6 and bring them into memory. We need to pick a page of physical memory to put them in. We're going to look through and see which one of our pages is the least recently used page. And we're told here that it's actually virtual page E, which corresponds to physical page 5. Okay, so are we ready just to slapdash bring in virtual page 6 and go blat and just stick it into this page here? No, so there's something we need to do. So I saw a couple bobble that way. So what do we need to do?
The dirty bit is 1 for 5.
Right.
We need to write that down.
Right. So how did the dirty bit get to be 1 for page 5? We're already on, working on page 6, and all of a sudden we're concerned about a dirty bit for some previous operation. How did that dirty bit get set? What was there about the program that caused the dirty bit to get set for virtual page E? We're sort of looking at an example. We're about ready. When we're done, we'll have the dirty bit set for virtual page 6. Right? Remember what the dirty bit's about? It means I have to do laundry. Dirty bit, dirty bit. What's dirty bit about? Someone would be brave. Yes, and what is the something way that we write into memory addresses in the beta? Store. Yes, there's been a store instruction that happened to address this virtual memory. Maybe somebody pushed something on the stack or something. So we can't just willy-nilly just throw the page away, otherwise we'll lose that state change. So we need to write it out onto disk. So what we're going to do is to go off. We're going to choose our replacement page. We're going to notice the dirty bit is 1. So I need to actually go ahead and mark write this out onto disk, and then I'm going to mark that virtual page E as no longer being resident. What I've done is I've gone off and I've written the information out on disk. And so now virtual page E is no longer resident. And you can see now I have a blank empty page here. It's not actually blank. We don't bother to zero it out because we're about ready to overwrite it with the contents of virtual page 6, which we bring in. And now we have to finish the process by setting up the page map so that we actually make virtual page 6 map to physical page 5. It's now resident. And by the way, it's also dirty because we just did a store instruction. So that's the whole process. The middle part of this is all executed by the page fault software, inside the kernel. And that happens again and again and again, many, many, many times. Okay, questions about so those are you should be able to sort of play memory management unit. Thankfully not for the quiz tomorrow, but in quiz 4 you'll almost certainly be expected to, given a little example like this, to work through what has to happen in order to complete different accesses, what pages are touched, what pages are written to disk, things like that. But if you just sort of think about the recipe and follow it, you should be able to get to where you need to go. Okay. So let's pop up a level and say, okay, I've seen the examples, and I promise to go off and learn how the memory management unit works. I'll do a little bit of practice. What do we use them for? How does this work? Why do we have them? And the answer is that we can think of this as basically the context in which this program was running is partly captured by this page map. And so we're able to adjust, its location in memory, where they, bring things on and off of disk. In general, we can start running the program without bringing everything that belongs to the program into memory. And in fact, you discover this a lot, right? So think a little bit about, so if you've just turned on your operating system, you type Python. Have you ever noticed this little pause? I mean, it actually seems to take a moment to start Python. And the answer is we're busy paging all the bits of the Python interpreter off of disk into memory, into physical pages. If you quit and you type Python again, it's like that. Whoa, what was special about the first time? And the answer is, well, all those pages are still on disk, and if you haven't run other programs still in memory, although you haven't run another program to cause them to be kicked out, then there they are, they're ready to go. So this notion of bringing things off of disk, you sort of experience that. You may not have noticed that but next time somebody says, why is there that little delay? You say, oh, it's paging from disk. Well, very, very erudite. Okay. All right, so the big idea, and this is what we're really going to spend the rest of today's lecture exploring, and some of next week's Thursday's lecture, is that we can have multiple contexts, and we can have multiple programs sort of running, if you will, running at the same time. They don't actually run concurrently, but we can alternate. You get a turn, then I get a turn, you get a turn, I get a turn. Time sharing, but we can all we don't have to keep moving information to and from memory, we just have to change the context so that when I'm running and I say 0, I get to a different page than when you're running and you say 0, and we can coexist, and in fact we don't really know about each other. What we're going to be busily trying to do is create a virtual machine. Okay, the whole idea of a virtual machine is that we write our programs as if each of them feels they have an entire, in our case, beta or x86 or whatever, is to ourselves. We have a whole bunch of address space, we have access to files and all sorts of I/O and things like that. In reality, of course, we have many, many programs that are sharing, each of whom is in blissful ignorance, thinking that, oh, how nice if I have a whole machine to myself. Okay, when in fact there's hundreds of them sharing a particular CPU. So we have this notion of a process. So we call these sort of running programs a process, and most machines have many processes. Somebody here has a laptop open. If you have an Apple, look in your activity monitor. If you have a Windows machine, look under Task Manager, and tell me how many processes you see running. What's your guess? 3? 700? 235. So there's hundreds of processes that are typically running on your machine. And the reason this like that is it's actually it's the easiest way to imagine how to get lots of things to happen without worrying about how they interact is you give each of them their own little machine to run in, and then they don't have to worry about the other ones, right? So processes are basically an abstraction which gives us a machine to run on, and we manage. What we're doing is thinking about the system architecture and the hardware that lets us to implement that abstraction very, very efficiently. So we can run hundreds of processes, reasonably well, and we'll see how that works. Okay, so here's sort of the scheme. So we have all this actual hardware along the bottom here, and then we're going to start talking about the notion of an operating system, of which Unix or Linux are examples. Windows 10, the Mac OS, these are all basically collections of so-called kernel code whose job it is to basically figure out how to share the hardware among many individual processes. And what's offered to the processes, in some cases, is pretty simple in the case of sharing, like the CPU. We simply give you a little time slice. We'll run you for 10 milliseconds, and then we're going to run some other process for 10 milliseconds. And we just give every process in a round-robin fashion a chance to run. As it turns out, of the 200 and some odd processes you found on your machine, only a small number of them tend to be runnable at any moment. Most of them are waiting for something, typically some sort of I/O wait. They're waiting for the next sector from disk, or they're waiting for the next network packet, or they're waiting for you to get back. They're waiting to wake up and check to see if you have mail. But mostly they're sitting there going, call me in a little bit, but don't run me now. Okay, some of these things, like virtual memory or Windows, are abstractions supported in hardware of the actual, of what's really available here, right? And so for instance, when you have a window, you just think of it as a rectangular region of pixels. It's really up to the kernel's windowing system to figure out what pixels are visible and to take the bitmaps that you're writing in and actually get them composed on the screen in such a way that if you have one window on top of another, the right thing happens. So what we do is we tend to try to give very good abstractions, usable, simple abstractions to the programmer. For instance, with a disk, we say, look, you have a file, contiguous region of bytes, keep adding to the end, you can open it for reading, give me a name, and then the kernel contains lots of code that maps that into actual disk sectors, and it worries all about which disk sectors belong to which files, and if you need another, you're writing it to the end of the file, where does that disk block come from? That's all managed. You're just dealing with these nice, clean abstractions. And of course, what we want to do is to arrange to have many such processes ready to run. So for now, what we're going to do is spend some time thinking about the whole notion of basically time sharing the processor among many, time sharing the processor, the hardware, among many processes, which are the sort of our abstraction for a virtual machine. Okay. So I like this diagram, the sort of dovetailing aspect of it sort of appeals to my woodworker. So remember that virtual time is basically going straight down the screen. In other words, for every process, they just think of themselves as running continuously. Right? In actuality, we're jumping around. So real time is taking this rather convoluted path, spending a little bit of time in process 0, a little bit of time in the operating system, and some more time in process 1, and vice versa. So we're taking this, this thread of real time and actually running around to create all these virtual threads of sort of virtual time. And so here's how the scheme works. We're running in process 0, and we're going to come, so here we are, running right where my arrow is. And at some point, we come to a point where we're going to interrupt that process, either because it explicitly asks the kernel to do something, so it's going to transfer directly to control of the kernel, like it says, open a file, or read me a character, something like that. Or there's a timer that goes ding, and the kernel says, I'm sorry, your time is up. I'm going to go run somebody else. So there's a way to create sort of an unforced, an interrupt that doesn't depend on program execution. We can interrupt a process because the kernel itself has this magic, doorbell that gets rung every 60th of a second, and it goes off and says, okay, time for somebody else to run. So we tend to, what the kernel is doing in this little stretch here is it's mothballing all the information for process 0. What is it I need to save away for process 0? Well, we have the physical pages that it occupies. Those, if we don't touch them, will be fine. What other things go with a process? What's some other state? Think of your running beta programs. What else is there about the program that you would have to save away in order to guarantee to be able to restart it again reliably? Program counter, yeah. All the register values, and so we actually, our interrupt mechanism carefully copies the program counter into a particular register. So our way of saving the program counter is we put it in XP, the register 30, and then we just use the register save mechanism. So there's a certain, so mothballing is not a terribly, be fairly thorough, but everything that's related to the state of a running process is packaged up and saved away in a kernel data structure, and then we go to a different process's data structure, reload everything, okay, and then start executing it. So when we resume execution from that interrupt, instead of returning to the interrupted code, we actually restart some other thing. Programs can't tell that they've been interrupted, okay, all their state is, between one instruction and the next, all their state is exactly the same, even if somebody else has run. If you were going to write a program to tell, okay, if you'd been interrupted, what would you have to do? You can't just look in your registers because we've been very careful to put all those back. Yeah. Yeah, you have to look at real time and say, whoa, 2 o'clock, where did that go? I've often thought students are sort of like that. Whoa, how did it get to be midnight? What was I off doing? Okay, so that's sort of the process, and the process, right? Sorry, too many. That's the recipe we have for switching from one process to another, and now we're going to look at some details. Okay, so what I have here is sort of a diagram which I'll be slowly filling in, which here you can see that we have a set of user processes, all in tasteful lavender. And so they're running some programs. The so-called SVC thing that you see here is actually a supervisor call. We'll get to those towards the end of this lecture. Here's the kernel, which is, if you want to think of it, just a separate process that runs every now and then in response to either external stimuli or timer interrupts. Here's the timer. Every 60th of a second, we create an actual IRQ signal that says interrupt. And if we're in user mode, the user mode program will be interrupted and we'll start running code in here. These yellow things are some data structures in the kernel. We have one so-called process control block that's associated with each of the running processes. So that's where we're going to mothball the state. So it includes a copy of all the user registers and other information, where you are in reading certain files, the file descriptors of the files you have open, what windows are accessible to you, and where their in-core bitmaps are. All of these things are all stored away as part of the process control block. Here is just a simple little scratch area where every time the kernel gets control, the first thing it does is take all the registers and copy them into the yellow space, into this little M state, machine state data structure, which that's sort of a temporary holding location, so it can have some registers to actually run the kernel code, because it wants, kernel code wants to load things into R0, and it can't do that until it's saved away the user's R0. So that's where that's going to go. Okay, and so our goal is to figure out what code we need to write in order to run these user processes in a round-robin fashion. Process 1, process 2, process n, and afterwards we're going to come back and start over again. Okay, and that's how your 235 processes are being executed. We're just going to say, your turn, your turn, your turn. And we're being fairly even-steven about it. Fancy operating systems have, priorities, and some processes get to run more frequently than other processes, but those are all bells and whistles over a basic round-robin time-sharing mechanism. So everybody gets sort of the basic plan. We're going to figure out how to write the operating system code. We're going to look at kernel code for a while now. That will arrange for us to run processes one after another. Okay, so the key technology is interrupts. You proud implementers of your very own interrupt mechanism. And in Lab 5, there was an external IRQ signal, which is what the timer is connected to, and every 60th of a second it makes IRQ go high. If you're in user mode, so that's notice in PC31 is 0. What we're going to do is basically do a forced procedure call in which we save the PC plus 4 into the XP register. That's what all this is about. And we're going to transfer control to a known location in memory. And that will be where the next instruction comes from. So keep in mind that the instruction that we interrupted has not been executed. We stopped it before it executed. We decided to execute something else instead. So when we return, we're going to have to remember to return to the user mode program in such a way that we're going to actually execute the interrupted instruction. Okay. Alrighty, so what we have here is a set of low memory locations. Whoops, too many clicks. Low memory locations which are devoted to certain sort of activities that are forced on the kernel. So the first one is the reset vector. We call these vectors because almost, you can say, wow, I could write a one instruction program to deal with reset or to deal with an illegal operation or deal with an interrupt. And you're saying, gosh, it would have to be a pretty good instruction, right? So, of course, we can't fit anything meaningful in one instruction because each one of these are consecutive memory locations. So, of course, what we actually put in is a branch to all the code we're really going to run. So low memory in our little tiny operating system is actually full of this little vector of branches, each one of which dispatches to the code that deals with the timer interrupt or the page fault or the supervisor call or whatever it is. Okay, so the basic, you'll see this in the code. We're going to take all their users' registers and put them into a kernel data structure we call mstate, a machine state. We're going to execute, do whatever the kernel has to do, and when it's going to be time to get back to the user, we're going to load all of this information back into the user registers, and then we're going to jump. We're going to take the contents of XP, which remember was the PC plus 4. So that means that if we want to re-execute the interrupted instruction, we have to take the value in the XP register, subtract 4 from it to get back to the address of the instruction we so crudely interrupted, okay, and resume execution with that instruction. And then we're back into user mode. Okay, I talked a little bit about where to find the handlers. We have a very simple built-in scheme. More exotic hardware, something that wasn't just meant to get the job done, but was might include having a very complicated set of tables for the interrupt vectors, depending on what priorities the interrupt's coming in on. Some of this we'll talk about in future lectures. Okay, so here's the scenario we're going to program, we're going to write the code for. What we have is the operating system maintains a time of day. And so its job is every once in a while, every 60th of a second, there's an interrupt. Bing! Okay, and it's time for the operating system to go increment the time of day by, a 60th of a second, and then return to the user program. The user program is completely ignorant of the fact that the kernel has borrowed a handful of cycles to go do whatever we're supposed to do on a timer interrupt. Right? So our whole mechanism is designed to make these virtual machines are really insulated from the interrupt systems and all that. So we use the hardware interrupt mechanism to transfer the control to the kernel, but then we're very careful to make sure that we can restart the user program without any visible part of the user being able to tell. Of course, the user may be able to ask the time of day of the operating system just to check, as Adam pointed out, whether time has passed. This is my last instruction. So we do have we need to come up with a way for the user program to communicate with the kernel, but only in a very controlled fashion. We don't want you jumping willy-nilly into random kernel code. Goodness knows what security holes there would be. So we want to have a very controlled interface but that will allow you to ask the kernel to do things, but only in very specific ways. And that's the so-called supervisor call, which we'll get to. The interrupt routine has its own little job. Its job is to save state, increment the time of day, and then return back to the user. So let's look at some code. Here's some actual code. You can see that it's a mixture of C and assembly language. Typically, we don't want to write in assembly language. For those of you who suffered through Lab 4, you probably all agree with me. It's like, okay, there's got to be a better way. It's hard to imagine computer scientists, lazy as we are, would put up with that much work. And the answer is, you're right. And so, in fact, that's why, Dennis Ritchie invented C. He wasn't going to program his operating system for his PDP-11 computer in PDP-11 assembly language. Thank you very much. Okay, so there's a little stub here whose job it is to sort of get the ball rolling and then to go off and call the actual handler code in C as quickly as possible. So here's what happens. This is the actual handler written in C. Down here, there's a branch in location 4 that says, please go to the clock handler code, so branch clock H. And what this guy does is, the first thing it does is this magic set of 31 stores. And what are those 31 stores devoted to doing? And how come it isn't 30 stores or 37 stores? There's something magic about 31. Well, according to Douglas Adams, 42 is the magic number. Yes? Yeah, so there's 31. We don't have to save our 31, the 32nd register, because it only reads a 0. So we're taking the 31 read-writable user registers and we're putting them off into this user data structure. This is this. So you see up here this data structure here called. You have to read C a little bit, not really, but if you read C, what this would tell you is that this is a particular structure of the type M state, and inside is a little array of 31 ints to hold the 31 register values. And we've happened to call the particular instance of this struct user. So we're accessing a particular instance of the M state struct and filling in all the register values. We go off and we're not really going to trust the user to have left the stack in any good state, so we set up the stack pointer so that the kernel writing, the sort of procedure return code that we're used to can use the stack to put in arguments and things like that. So we set up the kernel stack, and then we basically do a procedure call to clock handler. And then when it returns, our job is to go ahead and simply restore the user state, subtract 4 from the XP so that we will re-execute the interrupted instruction, and then return to the user with a jump. Everybody good with all that? Okay, so what happens here is that we call clock handler, and there is no really notion of an external in this particular very simple piece of hardware. There's no notion of an actual clock that you could go read and say it's a 142. It's just that it's like dead reckoning. I'll just keep adding. You'll contact a time server, you'll get the number of milliseconds since the epoch, you'll put it in a number, and I'll increment it by a 60th of a second every time it goes off and hope that I don't diverge too much. Once a day I'll go talk to the time server again and resynchronize my notion of what time it is with what the world thinks. But mostly computers are sort of muttering to themselves to keep track of their own time. Okay, so here we go. Increment this. So this is actually the key to time sharing. Okay, so the question is, how do we parlay this very simple mechanism into a time sharing mechanism? What I want to do is periodically move from running one process to another, and voila, miracle of miracles, mirabile dictu, as they would say in Latin. What we have is a periodic interrupt. So we're going to use the periodic interrupt to let us do periodic actions. And so in addition to simply incrementing the time of day, every so many quanta, so many ticks, whether it's 1 tick or 10 ticks, or every so often we're going to say, wait a minute, in addition to incrementing the time of day, I am going to go off and in this case run a very particular periodic action, which is the scheduler. The scheduler is a little piece of software whose job it is to figure out which process runs next. So whenever you see a call to scheduler, we're basically saying, okay, dear kernel, please go off and run somebody else for a while. In this case, we're doing that because this process's time is up. We're about ready to go run some other process. So here's the scheduler code down here. Here's that M state data structure, the user data structure that has all the temporary safe registers. And here's a structure that one of the things it has some information about the page map, about the current display number, what files you have open, things like that. It also has a copy of the 31 register values. So this is basically everything we know about the process, and we have a table. We're supporting n such mothballed pieces of state. And so what the scheduler does, okay, so yes, I should have been pressing the button, but didn't. What the scheduler, so we also have an index that tells us which process number we're currently running. So what the scheduler does is sort of the fun. So here, let me just see if I can. So here's my user data structure here, and it has copies of the 31 registers. And then over here, I have my big process table. Okay, so there's n of these guys, and for each process, I have a copy of its registers. Just draw something a little different because everybody's registers are a little different. So what's going to happen is if the current process was so this is process 1, process. So if cur is equal to 1, the first thing we're going to do is to take the registers that we saved away on the interrupt, and we're simply going to find an eraser. What we're going to do is to basically copy all of this information into that block. So that's what this statement does here. So take all this user information, the copy of this particular data structure, and put it into the mothballed, the permanent storage for that process. We're then going to increment cur, mod n. In other words, we're going to make this into a circuit buffer. We're going to start saying, oh, we want to run process 2. And so the next thing we do is we go off and load up process 2's registers. We don't actually change what's here, but we just that's what gets put into this data structure here. So that's process 2's registers. We're ready to now, and now we're going to, and then we deal with changing the page map and all that sort of stuff. And now remember, when we return from scheduler, we return to the end of the clock handler. Let's go back. We've just finished this call, so we're going to return from this thing, and now we're about ready to execute this code here to return to the user. And what are we going to do? We're going to take all this information and put it into the registers. And what information is this? This is process 2's registers. So we've set up the page map now so that the virtual to physical address translation is for process 2. And so we're really just on the verge of, we think, the hardware says, I'm just returning. I'm returning to an interrupted program. But we're not returning to the program we just interrupted. We're returning to the program we interrupted a long time ago, but now it's getting its turn to run again. Right? And so the sort of shuffling around of all this state is how we're going to execute going from one process to another. Boom, boom, boom. Round robin scheduler. Now, a few technical details. One is that, remember when you wrote your, a common failure mode is that on test, 434, your beta is working great, and you say, this is time for sure, and you run it, and somewhere towards the end, there's two little interrupts, one of which happens in kernel mode and one of which happens in user mode. If you took the first interrupt, if you tried to respond to IRQ in kernel mode, you ended up with an error and you had to go fix it. Right? So the idea is that we actually look at the high order bit of the PC, which is where we keep track of whether we're in user mode or kernel mode. We allow interrupts in user mode. In other words, we can interrupt any user program. For instance, the timer can go off and interrupt a user program. Once we're in the kernel, interrupts are disabled, so that what we would say in computer science terms is we would say the kernel is not reentrant. And this is really just a complexity saving feature. The idea is that there's nothing conceptual about allowing one piece of kernel code to somehow interrupt the running of another one. But it's very convenient whenever you take a kernel interrupt, for instance, to use this M state to save all the registers in. Well, obviously, and leave it there until you're ready to return. Obviously, that wouldn't work if every time there was another interrupt and you say, wait, I'm going to overwrite the stuff you saved before. So there'd be a lot of scurrying around of moving things from where they were saved to where they'll actually be safe and so forth and so on. So it's just better and it's simpler to allow the kernel to basically not take interrupts. However, this brings up some interesting behavior. How many have had your machine go absolutely, it's not working anymore. It's just dead. Yes. I'll raise my hand about 800 times. Yeah. And the reason, and you look at this and you go, what happened? There's no error reports, there's nothing. It's just not, it's not responding to me. And so what's the fix, of course? Where's the power button? Yeah, okay. And so the idea is that what's happened is either through some bug or something, you've gotten into a loop in kernel mode. No one's taking any interrupts. Nothing's happening. Your machine is basically never going to pay attention to you again. Okay, until you, of course, you restart it and wish that you had been saving that term paper a bit more frequently. Okay, so okay, so everybody sort of get the idea here. So no interrupts in kernel mode. So you have to be very careful with kernel code. It has to be right because you don't have much of a chance if you get stuck in the kernel, there's nothing to do but to power cycle your machine. And the other thing is that typically you don't want to spend very much time with interrupts disabled because you have a lot of I/O coming in and out, and the latency of responding to their requests for service affects the behavior of the network and of the disk and things like that. So in general, most kernel code is short and sweet. Okay, so we've talked a little bit now about how we go between processes, but suppose I was a process and wanted to ask for the time of day. How would I do that? But remember, I am in my own virtual machine, and the kernel code is there in physical memory somewhere, but it's not available to me. I just can't do a subroutine call to it because there's no address in my user mode program that corresponds to a location in the kernel. That would be very dangerous. So how do we do that? Well, we're going to invent a new mechanism called a supervisor call, SVC, supervisor call. And the way we're going to pass, we can pass information on our stack, we can pass information in the register. So if our kernel call, if this procedure call to the kernel involves arguments, we'll come up with various ad hoc mechanisms for getting it in, making sure the kernel can have access to that. The kernel can access all the user space, but nobody in user space can access the kernel. And we are going to implement supervisor calls rather than adding more hardware. We're simply going to use an illegal instruction, which we already know will cause the machine to take an exception. Okay, so here's what we're going to do is we're going to basically write a little handler for illegal operations. That's down here. And its job is to say, wait, is this an illegal operation that turns out to actually be a crypto request to write a character or to get the next key from the keyboard or to let somebody else run for a while? And so the way we're going to actually do this sort of remote procedure call into the kernel is to simply execute an illegal instruction, and a particular type of illegal instruction will be recognized as a supervisor call. So we already have the hardware that if you have an illegal opcode, remember how your control ROM was full of everything's an illegal opcode until you make it legal by changing the contents of that memory in your control ROM? This is the illegal hardware. So it's just like the interrupt, except we go to a different location in main memory. We go to 8004. And notice, even though we were in user mode, the PC that we put in, the new value of the PC has that high order bit set. That's what that 8 is at the end. If you've always been puzzling, why the hell do all these things begin with an 8 instead of a 0? The answer is that's the supervisor mode bit. Whenever you're transferring control on an interrupt or an exception, you are going into kernel mode. That's how we get into kernel mode. That's the only way to get into kernel mode is through one of these exceptions or interrupts. There's no other mechanism to get into kernel mode in the beta. You have to do one of these special exceptions or interrupts. Okay, so here's location 4. It's going to go ahead and, so this is all part of, we have a little, Lab 7 is a little tiny operating system. You get, it's a little time sharing system. It actually has 3 processes which translate things in Pig Latin. Obviously a crucial data computer science task that we're going to be able to do. You actually get, it runs pretty, so our beta simulator runs at several million instructions per second simulated, so you actually get to sit there and fool with it. You will actually be modifying the operating system to add another process. You'll be giving it its own process control block. You'll be writing your own code. You'll be writing a new device handler. You'll be actually adding all sorts of little bits to our operating system. So sort of fun for those of us who like that sort of thing. What was it, Abraham Lincoln sort of? If this is the sort of thing that you like, you'll really like this thing. Yes, okay. Okay, so the idea of the ILOP handler, it first of all has to separate real illegal instructions from the so-called supervisor call. So it's busy extracting the opcode and using it to select which one of 64 routines to execute. Mostly the 64 routines are the thing that print out the blue screen of death. How many of you have experienced that wonderful Windows? You know, the screen is a beautiful shade of blue, right, with white lettering, typically full of large cryptic hex numbers. Okay, in which case you look at it and you say, this is really useful, except I feel like shooting myself because I have to start over again, whatever it was. So I'm sure that information is really useful for somebody, but for most of us it's just, you know, okay, loser, you get to start again. Okay, so this is the blue screen of death code. A particular one of those opcodes, in fact, opcode 1 is our signal to go off and do a supervisor call. And so what we see down here is an actual, we use the low order bits of this illegal instruction to tell us which one of our 8 supervisor calls we're going to execute. Okay, so what I'm going to do, I'm going to stop there. We're going to pick it up again next time. We're going to have fun writing some device handlers and actually see how it is we can interface with the devices. Good luck on the quiz.